What's up, guys? In this video, we're going to talk about evaluating the limit. I went through my back catalog and found 50 different examples of me evaluating the limit. So to teach you how to evaluate the limit, we're going to start off with examples of evaluating a limit from a table. Then we're going to work on evaluating a limit from a graph, how to evaluate the limit from the difference quotient, and then we're going to get into equations. We're going to work on evaluating the limit from polynomials, absolute value, radicals, piecewise functions, rational functions, complex fractions, exponential, logarithmic, as well as trigonometric limits. So this is all contained. It's a ton of examples, but if you follow this video from beginning to end, you're going to have an excellent understanding of how to evaluate the limit. These examples were handpicked for your understanding, so I hope you enjoy. Cheers. So when we want to evaluate the limit, we're looking at as x is approaching 5. So again, the top values is x, right? And that's what we're looking. And again, for the limit to exist, we want to see what is it approaching from the left and from the right. So as x is getting closer and closer to 5, we know 5 is right here, right? It's not in the table, but we know it's there. And we want to see what the graph is approaching here from the right-hand side, right? And we want to look at the values that we see it's approaching. And I can tell you guys, it's going to be like an estimate, of some sort, because we don't know what exactly the value is. But can we make a kind of good consensus on what we think the value is as it's? You can see these numbers are getting larger, larger. Then here, the numbers are getting smaller and smaller. And it looks like they're getting really, really close to 3, right? It's kind of obvious. Over here, though, kind of throws you a little curve, because we know what the value of 6 is. The 6 is in the table, 7.2. However, remember, the limit is not saying what the value is. The limit is saying what is the function approaching. So as x gets closer and closer to 6 from the left and from the right, what y value, 0.8, 0.99, 0.99, looks like this is getting really close, not really to 7.2, though. And from the right, it's getting really, really close to a number. What number does it look like it's getting really, really close to? 1. OK? So even though the function is evaluated at 6, it's approaching 1. And that's what we're looking for when we're looking at the limit, is what is it approaching from the left and from the right. That make sense? OK. Perfection that these are going to be 3 examples of continuous functions. So to evaluate for the limit, what the value of what the function is approaching as x approaches -3, as x approaches 2, and as x approaches 4, we can simply just plug in the value. So I'll just take -3 squared minus 8. -3 squared is going to be 9 minus 8, and that's going to equal 1. Over here, I'm just going to take 2, plug it into the function. So I have 2 cubed minus 2 times 2 squared minus 10. Please note how I am using my use of parentheses as I am plugging in those values. So therefore, I have 8. This becomes -2 times 4 minus 10. So therefore, that's 0. So I'm equal to -10. OK. And again, ladies and gentlemen, we can go ahead and graph each one of these. So you can visually go ahead and see where this is approaching. And then lastly, we have x as approaches to 4. So we'll just do 3 times 4 times the square root of 4. 12 times 2. 24. So what something you guys might see here is we might tell you here's f of x. Or a lot of times you'll see limit as x approaches 1 of x minus 1 squared plus 2. So if we need to evaluate the limit when x approaches, so what this says is as x approaches 1, and remember x is the input value, right? So as x approaches 1 of this function. So we already did that, right? You guys did your table. We created a table of values from the left, and we created tables of right. And we kept on getting closer and closer to 1, right? We approached it from the left and from the right. And as what we saw, by approaching it from the left and the right, we came up to our value that was equal to, what was it approaching from the left and from the right? 2, right? So I don't, obviously with the technology, you guys can see, you guys saw it from the table values. You can also just look at this graph. This is a continuous graph. So from the left, as x gets really, really close to the number 1, right, we're getting closer to the output value of 2. And then from the right, as we approach, as these dots, as the x values get closer and closer to 1 from the right, you can see, again, we're approaching this value of 2. Does everybody see that? OK? So the kind of trick, though, is when we know we have a continuous function, we know there's nothing crazy going on. All we really need to do is just find the value of the function of what it is. Right? Does that make sense? You just really need to figure out the value of the function. So when you guys look at the constant function, we got to figure out what is this function? What is, forget about the limit stuff. F of x equals 13. How do you graph f of x equals 13? Well, remember, guys, function notation is very similar to like y equals 13. So back in algebra 1, how do we graph something when y equals? It's just a horizontal line, right? Because here's your y, here's your x. Y equals 13, so you go up to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So again, we're trying to find the height of this function at x equals 5. So let's go over to 5. 1, 2, 3, 4, 5. Are we approaching a value from the left and from the right? Yes. And since this function is continuous, I need to plug it in. But can you plug in 5 into this function? No. But do we know what the height is? Do we know what the value is at 5? It's just 13. So that was your limit. OK? So if I was given this graph, and let's just kind of do one by one. If I said, what is f of 1? That means we're looking for the value of the function at f of 1. So we go to 1, and we say, what is the value of the function? Well, the output value, right? That's the value of the function. So we find the y value, or the f of x value, and we see that it is equal to 2. So we say f of 1 is equal to 2. Now the limit is something different. The limit is saying, what is the value approaching as x gets closer to 1 from the left? Remember the table? From the left as well as from the right. So you can basically kind of take like your two fingers and kind of like squeeze the graph and say, all right, from the left and from the right, what y value or f of x value am I getting closer and closer to? Or am I approaching? 2. Oh, OK, well, that was easy. All right, I'm done. That was it. Yes? Same answer. But it's not always the case. Let's look at the next one, f of 0. We go to f of 0, and we notice there's a hole. So we obviously know that it's undefined there. But there is a dot here that is being in replacement of that. So therefore, at f of 0 is equal to -1.
So it doesn't jump, but then it does.
It's a hole. That's a hole. Right? It's not available there, but it's available there. Yes?
Or it could be just a double jump.
No. So now the next thing is let's answer the limit question. The limit question is saying, but then what is the value that the graph is approaching? So again, we follow our fingers here, and we see that it's approaching, not -1. It's approaching what? +1. So notice these answers are different. They're not the same. The value is not the same as the limit.
So it doesn't matter if there's a hole there?
No, it's where it's approaching, not the actual value. Let's go and look at f of -3. So we go to -3. F of -3 is not up there. That's undefined, right? That's a hole. That's the filled in line. So that's going to be also -1. However, where is it approaching? Well, from the left, it looks like it's approaching 2. From the right, it's approaching -1. So is it approach? Can we write 2, -1 like some people did up here? No, right? You can only evaluate one number. So since it's approaching 2 different numbers, it does not exist. And then the last one, guys, we have f of 2. Well, we go to 2. That's obviously an asymptote, right? Asymptotes are undefined values. So that does not exist. And now we look at this and we say, oh, well, it's approaching positive infinity and negative infinity. It's going in 2 different directions.
So when it says f2.
That's the value of the function. So again, that does not exist. OK, so that is your basics for evaluating from a graph. So in this case, we have the limit of f of x as x approaches 3 from the left-hand side. So basically, we're following from the left-hand side. And as we go, as we approach 3, we see that the f of x value is going to equal 1. When we approach the limit from 3 from the positive side, we're going to the right of 3. And we're going from right over to left. And we can see that it approaches the f of x value of 3. if we're just going to find the limit of the x equals 3, even though the function is equal at 3, we see that the left and right-hand sides are not the same. The function is not approaching the same limit from the left and right-hand side. So we can just write does not exist. However, if we are going to plug 3 into the function, even though we don't know what these functions are, we know that this solid dot represents that that is the value that the function is equivalent to at 3, which you can see the value is 1. Anybody have any questions on this little warm-up? No? OK. All right. So here we have a function. And the function is labeled g of x. And what we're doing is I gave a whole bunch of limits. Now, in this one, I'm not just doing general limits. I did left-hand limits, right-hand limits. So what we're doing is we're looking for the value that the function is approaching, the y value that the function is approaching, as x approaches different values. OK? Now, again, just remember, guys, when you have that little like negative up there, that's saying it's approaching from the left side. So you find the value, like -4, and you say, all right, so as I approach -4 from the left, which is like my left hand, you can see that, well, from the left of -4 is over here. So as I'm approaching -4, x value -4, from the left, I'm getting really, really close to what y value?
4.
You're approaching 4, right? So we could say the limit as x approaches -4 from the left is equal to 4. So we just write it and read it as x approaches -4. And then the reason why the left is like from the left. X approaches -4 from the right. That little plus just means from the right-hand side. So yeah, I would avoid just doing something that's not, at least their standard notation. So now let's go and take a look. What about as we approach -4 from the right? So we look at our graph, we kind of take our right hand, and we say, all right, well, let's follow this graph from the right. As we approach from the right, we get really, really close to what y value? -2. Now, this is helpful because if we want to identify what is our general limit, the general limit is the value that our function approaches from the left and from the right. And what we notice is, if I want to find the limit as x equals -4, they don't apply to the same, they don't approach the same value, right? So guess what? The general limit does not exist. The limit as x approaches 0. Sometimes people are like, well, guys, limits don't always have to occur at discontinuities. At x equals 0, we have the function is equal to 2. But as you guys see, as we approach from the left and through the right, what value are we approaching? 2. So it's a little gimme in there. But limits don't always have to approach at discontinuities. They're more likely to approach at discontinuities for algebraic reasons, which we'll see. But they don't always have to go to there. Next one. What about as we approach -6 from the right? So as we're going from -6 from the right, we're getting really, really close to which y value? 0. What about as we approach the general limit from -6? So from the right, we're approaching 0. From the left, is there anything on the left? No. So is it even possible to approach from the left, or there's nothing there? Not really, because so since we don't have anything to the left, we can't approach from the left, right? And since our definition says we have to approach for the same value from the left and the right, this does not exist. 2 from the right. So as we're approaching the value of 2 from the right, now again, here's a hole. But again, guys, doesn't matter if it's a hole, doesn't matter if there's a point there. We're looking for the value which it's approaching, which is 0. As we approach 4, now this is an asymptote, right? But as we're approaching 4 from the right, you guys can see that we're going all the way up to infinity. And as we approach 4 from the left, or wait, this is just, as we approach 4 from the left, we're going down to -infinity. Well, since we're not approaching the same, since we're going in different directions here at 4, we can definitely say it does not exist. Now, technically, real quick, technically from 4 from the right still does not exist because you're not actually approaching a y value. Infinity is not a value. But a lot of times we give the direction that the graph is heading when we're approaching like an asymptote or like end behavior or something like that. Like we give the direction because the direction is more specific than does not exist, right? But technically, for positive does not exist because you're actually not approaching a value. Yes?
What if they get that equation on A to C? Would it be like
You wouldn't have like to choose between does not exist and infinity. No. So that's what I'm just saying. Like technically it does not exist, But we often rather you just label the direction. So we give you answer choices like infinity or negative infinity. Which actually brings up my point. This obviously does not exist because they're not even going in the same directions. But if my graph looked like that, then a lot of times we'd say limit as x approaches 4. You can see the direction from both sides is both going down to negative infinity, so we'd give the answer of negative infinity. Or you'd see the answer of negative infinity as an option. All right, so we're going to do the difference quotient, where we're going to simplify the difference quotient. So rather than making this very, very confusing, I'm going to try to make this as simplistic as possible. We see this crazy stuff right here. F of x plus h minus f of x all over h. It's just like, why am I doing this? Why do I have to do this? Let's try to simplify this as much as possible. First of all, let's just try to remember, if I was going to find f of 1, right? I would plug 1 in for all my x values, correct? If I wanted to evaluate this, right? So let's just try to think of this way. They're saying, well, rather than evaluating for f of 1, they want me to evaluate for f of x plus h. So I'm going to do the same thing. I'm going to multiply x plus h squared minus 2 times x plus h. Do you follow me? See what I did? All right. So let's go ahead and figure what this is going to be. All right. Remember x plus h squared. I'll break this down really good. X plus h. X times x is x squared. X times h is xh. X times h is xh.
Mr. Cutter, can you
H
please
times
call
h
Miss
is
Klein
h
at
squared.
1038? Mr. Cutter, please call Miss Klein at 1038.
All right. So when I factor that binomial, or when I expand that binomial, I now get 4 times x squared plus 2xh plus h squared. Follow me. So minus, now, let's just rewrite this, 2x plus h. Now what I have is, I can now do my distributive property, right? This is like a lot of steps. But the steps, hopefully you can follow. There's nothing new we're doing. I know it's like crazy, but we're just following steps. So distributive property. 4 times x squared is 4x squared plus 8xh plus 4h squared minus 2x minus 2h. It's pretty big, isn't it? It's a lot. But do you see what I have there? Does that make sense?
Yeah.
So that is this. I just did that, right?
Oh.
You see what I did?
Yeah.
I just did one part of it.
Okay.
So I just said, take this, what this was, this huge thing, and then it said subtract f of x. Well, what was my f of x? That's 4x squared minus 2x. So I take 4x squared, I'm just going to rewrite it all over again. xh plus 4h squared minus 2x minus 2h minus f of x, which is 4x squared
Kelly Click, please call the main office. Miss Click, please call the main office.
So you do negative 4x, of course, right there in the video. So negative 4x minus 4x squared minus 2x. Well, that can be, I can distribute that negative sign to make this a negative 4x plus 2x squared. All right? See where I'm at. Now that's that. Okay? So now I got that done. Well, what we're going to do, and what you can see is, those are opposites, right? Those cancel out. Got me? These are opposites. These cancel out. Right? So when I finish up this top here, I'm only left with a 4h squared plus 8xh minus 2h. Follow me. Then we got to put it over h. Right? Well, now what we notice is I can now simplify. I can divide this h into all of these. So what I can do is I can cancel these h's, cancels out, and cancels out. Right? Right? So therefore, my final answer is 4h plus 8x minus 2, and where h cannot equal 0. So that's all I want to do. What?
So that's easy.
There's going to be problems. There's going to be variables that you have never seen before. All right? That's kind of the purpose of what they do to create these tests, is things that they want to test your understanding, not just by, hey, can you find the limit of something that would have been similar to your textbook? No, they're going to test your skills on something that you've never seen before. So it's really going to be important for you guys to look at something like this and say, all right, I've never maybe seen or worked with delta x, but what exactly, again, is this problem? Well, they're treating delta x as just any kind of variable. You could use it as y if you wanted to, or z, or use a Greek letter if you want to. So it's just representing a different variable. So the main important thing is I understand that direct substitution is not going to work, but if I apply my operation, okay. Also notice, ladies and gentlemen, when you guys are doing these for your exam, to make sure, I've been kind of showing some work for time purposes of just kind of using the equal sign. But make sure when you use the limits, this is what we call our limit notation. For every line that you're writing the new limit, make sure that you also always include the limit notation there. All right. I'm going to remind you when you guys take your quiz, because that's one thing I want you to kind of practice on. And I'll let you know when that's something that's going to be requested. But you guys are only going to have a couple tests where we're going to need this. But when you guys take your exam, I will remind you, every single line you're going to have to rewrite the limit. So as delta x approaches 0, you guys can see that the 2x and the negative text do divide out. And you can also see, so that's going to leave us with 2 delta x over delta x. And therefore, now I have limit as my theta approaches 0 of 2. And therefore, when my my limit as approaches some number equals a constant, then my limit is always going to equal, remember, what should it equal? It's just going to equal your constant in there. I'll just leave it as that. What we need to understand when we're looking at them is you understand which limit definition we are talking about. Because remember, the limit definition is all really based on, we're either two of them, we're actually evaluating the derivative at a given value, and then the third one was just taking the derivative of our value. So in this case, if you guys remember the limit definition of x as h goes to 0, we had f of c plus h minus f of c all over h. That was the limit definition. That was a rule. That was formula that I gave you guys. This is a limit definition of a derivative right here. And basically what that was saying is find f prime of c. That's really what this is asking. So what we need to understand is, well, what is our function then? In this example, what exactly are we taking the derivative of? Well, our function in this problem, my f of x, you could say, is going to be ln of x. And then what is my value c in this case? My value c over here is going to be e. That's my c. So really what I'm doing is taking f prime of e. So the derivative of ln of x is 1 over x, which is really just going to be 1 over e. Yes? Wouldn't it be ln of h? Nope. It's c is going to be your value. So this is the same thing as f prime of c. Okay. Right like that. That's what that means. Okay? So as we approach 2 from the positive, so from 2 from the positive, go in here. What is the f of x value that I am approaching from the right-hand side? F of x value. What value am I approaching? F of x. I'm going down f of x, right? You're approaching the f of x value, which f of x value is up or down, which in this case is going to be 0. However, if you guys look at this, if we approach from the left-hand side, do we have a left-hand side? There's not even a graph on the left-hand side, right? It's not like it's not that it's not continuous. It is a continuous function, but there is no left-hand side. So this does not exist. And then furthermore, if we're looking at the general limit, if I don't have a function that approaches from the left and the right-hand side, then we can say that the general limit also does not exist. So this looks like a crazy equation, right? Probably none of you looked at this and said, oh, I know what the graph looks like. But it looks something like that, correct? So we know at 0, it's undefined. It doesn't look like there's any asymptote there, so there's some hole. However, what was that value? What is it approaching from the left and right? You could have looked at the graph, or you could have used the table. What value is it getting really, really close to from the left and from the right? What output, y value, is it approaching? 1. Oh, is that 1? What is that at negative? It's 2? OK, 2. So it looks like it's approaching 2. So does it make sense then that the limit exists at 0? Because it's just approaching. What is it approaching from the left and right? So that value is 2. What is it approaching just from the left? Just from the left, what is it getting really, really close to? From the left, what is it getting really, really close to? 2. From the right, what is it getting really, really close to? 2. Remember, guys, for the general limit to exist, the left and the right hand have to be the same. I'll say that again, because it's actually going to come up later in this section. For the general limit to exist, the left and the right hand limit have to be exactly the same. If the left and the right hand limits aren't the same, then the general limit does not exist. OK? Remember, like the absolute value on over x, they went to different. The left and right hands were different. So that means the general limit didn't exist. OK? So rationalizing the radical, doesn't matter if the radical is in the numerator or in the denominator. We're going to want to multiply by the conjugate. Again, looking over conjugate, the conjugate is the exact same expression, but with a different value. Or sorry, so if this is subtraction, then we're going to multiply by the conjugate, which is x plus 1 plus 2. And whatever you do in the numerator, you have to do in the denominator to produce equivalent fractions. OK? Oh, sorry. We can't use direct substitution here, right? Because when we just plug in direct substitution, it goes to 0. But the first thing you would want to do is check that. So now we go ahead and multiply. Now again, what's the square root of x plus 1 times the square root of x plus 1? It's just going to be x plus 1, right? Negative 2 times negative 2 is just going to be minus 2. Now, why am I skipping ahead? Why am I not doing the middle terms? Because what happened to the middle terms? They canceled out. Yes?
So why didn't we do it on the numerator and not the denominator?
Well, there is no radical in the denominator. So that's why, basically. We're trying to get rid of the radical. This is our basic idea. And then in the denominator, we're just going to leave this as x minus 3 times the square root of x plus 1 plus 2. X plus 1. Oh, I'm sorry. I multiplied that wrong. That's 4. Negative 2 times 2 is negative 4. OK? Now, when we go ahead and simplify this, this becomes x minus 3 all over x minus 3 times the square root of x plus 1 plus 2. Uh-oh. What happens with the x minus 3s? Yay. So now, as x approaches 3, I can just directly substitute 1 over the square root of x plus 1 plus 2 equals 1 over square root of 3 plus 1 plus 2. 3 plus 1 is 4. Square root of 4 is 2. So that's going to be 1/2 plus 2. Sorry. Ends up being 1/4. Wait a minute, that's plus 1. Yeah, and then you evaluate 3. OK, 4. Yep. All right, So in this case, ladies and gentlemen, again, we are going to have a little issue because if we apply the direct substitution, which again is the first important thing we want to do when evaluating the limit, we see is we have the square root of 5 over 0, right? Which is not going to, we're not going to be evaluate our limit for. So what we're going to want to do is, again, first thing is always apply direct substitution, which we did. And a lot of time you can just do those by inspection. You take off your hat, please. Then the next thing we'll want to do is look into factoring, right? Well, there's really nothing we can factor. And I can tell you a big key is whenever you see a radical, think to rationalizing out the radical. And basically, to rationalizing out the radical, we just need to multiply by the conjugate, which we kind of did a little bit of practice with last class period. In this case, is going to be x plus 5 minus the square root of x. And then whatever you multiply in the bottom, you have to multiply in the top. Anybody have any questions with what I did so far? Yes? Did I change the problem? So it's square root of 5. That's, wait, what? 53. Oh, it's just square root of, OK, this. Gotcha. OK. Does everybody follow me with what I did? Everybody see why that's the conjugate? Anybody have any questions on identifying the conjugate? Yes, it should be plus. That's for it's not the conjugate. Very good. All right, so now we have the conjugate. Everything looks good now. Anybody have any questions so far on what I have done? Okay. So let me just go back and remind you, ladies and gentlemen, if you had a minus b times a plus b, basically a number by its conjugate, this produces a difference of two squares. Remember, this goes a squared minus ab plus b squared. So it just gives us a squared minus b squared, correct? The middle terms divide out. So if you have a binomial times its conjugate, notice how it's the same thing as the difference of two squares. In reality, our middle terms are going to cancel out. So we have this term squared and this term squared. So when I go and set the equal this, x plus 5 times x plus 5, I'm sorry, the square root of x plus 5 times the square root of x plus 5 is going to be the square root of x plus 5 squared, which is just going to leave me with x plus 5. Negative square root of 5 times positive square root of 5 is going to give us a negative square root of 5 squared, which is just going to leave me with a negative 5. And then over here, I'm not going to distribute this through. I'm just going to leave it just like this. Obviously, you guys can see that the 5s divide out. The x's divide out, which just leaves me with 1 over the square root of x plus 5 plus, how did I do this problem differently? Equals the square root of 5. And now we can go ahead and evaluate in for the 0, which now you can have 1 over 2 square root of 5. Which, let me double check, is my 1-353. I don't remember that being my answer. Yep. And there you go. They did in the book on the AP exam, you don't need to rationalize the denominator. So it's perfectly fine just leaving it as is. And I will accept it in both forms. But yes, in like algebra, we rationalize the denominator and so forth. But in the AP exam, which obviously we're concerned about, they're not going to care if you rationalize the denominator or not. OK? But we did have to rationalize the radical, though. That's the important thing. So in this one, some of you might be, obviously we know direct substitution one doesn't work. We might be tempted to look at rationalizing the radical. But when we go ahead and rationalize the radical, we're left with 25 minus x over x minus 9, which is not helping us out at all, right? So rationalizing the radical. Yes, question? Yeah, it is. You're right. Sorry. Thank you. Yeah. But again, does that help? Does that avoid our direct substitution? It still goes to 0, right? So doesn't change anything. Oh, that was technically it looks like that. All right. So rationalizing the radical doesn't help. But fortunately for us, they're asking us for what is the left and the right-hand limits. And since we're approaching an asymptote, then we know we can use smaller and smaller numbers. So if we're approaching 9 from the left, we can use anybody? Nobody use anything else? 8.9, OK. And again, guys, we're not looking for exact values. We don't know what the square root of 8.9 is. Do we know what the square root of 9 is, though? 3. So is 8.9 going to be smaller than 3? Yes. So 5 minus some number that's smaller than 3 is going to be positive. 8.9 minus 9 is going to be negative. Positive divided by negative is negative infinity. So the limit as x approaches 9 from the left is equal to negative infinity. OK? Lastly, ladies and gentlemen, I think these are very basic. Hopefully, if you guys remember from your pre-calculus class, you guys can understand that this is a continuous function. This is that V-shaped graph. So since you know it's continuous, all you need to do is plug in 2 into this function. Okay? However, since it's at the beginning, I just want to make sure I review the transformations and so forth for you, because this is going to come up in this chapter. So this is just a great opportunity for me to review graphing. Because yes, you could all plug them into your calculator. But the main important thing when you guys are graphing, let's just call this f of x. If you're graphing 2 minus x, and this shows up in the review packet that's being passed around, make sure you guys put this into the x minus h, and make sure you guys put this into that x minus h format. So what I would do is I would rewrite this as negative x plus 2. And then we have to make sure that if we're going to transform this correctly, we've got to factor out this negative. The negative needs to be actually factored out. So therefore, it's going to look like this. OK? Now what this tells us is if you're a review on transformations in pre-calculus and algebra 2, this is a reflection about the y-axis. And this is a horizontal shift 2 units to the right. OK? So if here's your parent graph, does reflecting about the y-axis change the graph? No. But the graph is being shifted over 2 units to your right. Now you guys can see, again, we're just evaluating the limit. And the main important thing I want to verify with you guys is you guys can see why that works. Because if I'm just going to, if we're evaluating the limit, is it continuous at 2? Is this graph continuous at 2? Yeah, so we just need to figure out what that value is, which you guys know is 0. So if we're going to evaluate this limit, all we simply need to do, the limit as x approaches 2, we just need to plug in 2. Plug in 2 into the equation. So the absolute value of 2 minus 2 is equal to the absolute value of 0, which is just equal to 0. OK? But I wanted you guys to see the graph, just so you guys need to visualize that, because absolute value comes up quite a bit. So you need to make sure we can visualize that. This is saying, what is the limit as x approaches 0 from the left? So again, I think it's helpful to look at the graph. As we look at this graph, ladies and gentlemen, as we go from the left, and you basically can look at your graph and kind of raise up your left hand and say, all right, from the left, what value am I approaching? It's not the general limit. You don't need to go from both sides, just your left hand. From the left, what value, output value, am I approaching? -1. So -1. What about from the right? What value am I approaching? 1. Well, you're not even approaching it. I mean, that is the value of it, right? It's not like it's kind of graphs. We'll look at some different graphs, and I think it'll help you guys out. But what I want you guys to see, yeah, from both of those sides, notice how the left and the right limit exists, but the general limit does not, right? And that's totally possible. Happens a lot. OK? All right, well, that's it on that. Now we're stuck at a point, guys. We have a function that is non-continuous. So when we look at this graph, when you guys plug this into your graphing technology, and please make sure you guys get the table too as well. you guys are going to have a graph that's going to look something like this. Okay. Now, obviously, at 0, it can't equal 0. Okay. So these are going to be open circles because you can't actually equal 0, right? Because if you had x equals 0, then it'd be undefined. So these are both. I should probably have some bigger dots here. These are both undefined at 0. However, when we look at the table, at -2, it's equal to -1. At -1, it's equal to -1. At, what the heck did I do? Didn't need that. At 0, it's undefined. At 1, it's equal to 1. And at 2 is equal to 1. Right? Am I great? You guys, anybody clear the table? Good? So let's go and think about this. It's a non-continuous function, right? You can't draw this function without having to jump and go on over there. So that's one issue that we have already. It's a jump discontinuity. Now, the next thing is, let's go ahead and think about evaluating some limits here at different values. So if I wanted to find the limit as x approaches 1 of g of x, okay? Let's say you want to evaluate the limit at 1. So let's go to where 1 is. 1 is right here. Now think about from the left and from the right at 1. Is that continuous? From over here, like if we're trying to approach 1, is it continuous? Right? And you can see that it's approaching it from the left and right. They're both, from both sides, it's approaching it equal to 1. Now we don't need to change our table, guys. But would you agree with me that if you did 0.9999, it's going to look really close to 1? And if you did 1.00001, it's going to get really close to 1? Right? Would you guys agree with me that from left and right, they're both approaching 1? And again, let's evaluate for 1. Right? So if I want to evaluate the limit as x approaches 1 of g of x, that's just going to equal 1. Look at the first one. Now, I think it's easy. I think it's best to understand what the graph looks like, or at least we can understand if there's discontinuities. Because if you guys remember when we looked at that graph, like there was discontinuities, right? And the only time the limit didn't exist is when the general limit didn't approach from both sides, or we had a jump discontinuity, right? Holes and stuff like that were fine, or asymptotes could be an issue as well. Well, we look at the absolute value graph, and we know the absolute value graph is that V-shaped graph, right? It's continuous. There's no jump discontinuities, and at least in this example, there's no holes, right? So we know that this graph is continuous on all values. Would you guys agree? Right? And actually, you guys should just notice the V graph but being shifted 3 units to the right. So I could even sketch this 1, 2, 3, like this. And that's what the graph looks like. Now, what the value is saying, limit as x approaches 0 of f of x, they're basically saying, what is the value of the graph as we're approaching x equals 0? Well, that's going to be like that dot right there. Right? So what is that value? How do we find that value? Well, basically, we're looking for the y coordinate when x is equal to 0. Right? So all we simply need to do, guys, is just plug in 0 in for x, and then find the value of y. Right? So the limit of f of x as x approaches 0 is going to be the absolute value of 0 minus -3, which is then equal to 3. Right? Yes? No? So that is what we call direct substitution. If you are looking for a given value and you can plug it in, well, then just plug it in. It's pretty simple, right? So the next one is the absolute value of x over -2 divided by x minus 2, which is like this function. However, if I subtract 2, that's another transformation. All that's doing is shifting the graph 2 units to the right. So now the graph just looks like that. We know that evaluating it at 2, is going to be a discontinuity. And we know that all I did is looked at the graph shifted over, so the limit at 2 does not exist. The limit from the left-hand side is still going to equal -1. And the limit from the right-hand side is still going to equal 1. The only thing that this x minus 2 did to our original parent graph is just shifted the graph 2 units to the right. Does everybody see that? OK. In this first example, guys, we're back to piecewise functions. So just remember, guys, when you're looking at a graphing a piecewise function, on a graphing calculator, there isn't like that nice little thing that you just type it in, right? So you got to remember, what are we doing with piecewise functions? Piecewise function is basically taking into account both of these functions. So we have the absolute value of x plus 1, which we can graph in our graphing calculator. But we should be able to graph this very easily on our own. And we can graph the equation -1. We could also do this in our we could also graph that in our calculator. But I think I can do this rather quickly. Remember, guys, this is the V-shaped graph, right? And then we have it -1. So those are the two graphs, right? So the V-shaped graph just being shifted 1 unit to the left, right? Transformations. And then y equals -1 is the other graph, which is just a horizontal line, which we've been pretty familiar with now when we did the conics. So now we've got to look at the constraints. The constraints here is to graph this function for all values except x cannot equal 3. So then we say, well, where is 3? 1, 2, 3. Right there, it can't equal whatever that function value is. We need to put a hole there. Right? So it equals all values on the domain except for 3. Then we go look at -1, and it says this function is only true at when x is equal to 3. So then the rest of the graph is not defined. So we just erase. So that is what our graph looks like. Then we ask ourselves the question, is that graph continuous or not? No. So we say no. And therefore, describe the continuity. We say that is a hole. Right? Next one, again, hopefully you guys recognize this as a quadratic. So I'm just going to graph both of them and then restrict them. So x squared minus 1 is just a quadratic that looks something like this. Right? Remember, the -1 is not shifting it to the right one. It's shifting it down because the minus is outside of the function. And then we have x plus 1, which is just a standard line. So we're going up 1, and then it's an up 1 over 1. So that's a rough sketch of the graphs. Now let's go ahead and look at the restrictions. So the restrictions are at -1. So at -1, this function is true. So now I'm not sure if I graphed this correctly or the best ability, but let's check out what should -1 be for this function. So -1 squared is 1. 1 minus 1 is 0, right? So this function is true right there. So that means the rest of the function is not defined. Does everybody see what I did, how I just erased the rest of that function? Because this function, this quadratic, is only defined for x values that are less than -1. This function is only defined for x values that are greater than -1. Well, at -1, what do I have? 0, right? So anything to the right here is going to be defined, except for at -1. However, I don't want to use an open hole because I already have it defined by the other function. So all I need to do here is just erase. So it looks like a weird little function, but is it continuous? Yes. So remember, guys, just because it's a piecewise function doesn't mean, oh, piecewise function, it can't be continuous. No, you can have them meet. Just the reminder, when you guys are looking at a piecewise functions, in this case, we have two breaking points. We have a breaking point at 1, and we have a breaking point at 2. And again, if I was just going to like sketch this graph, I have no idea if it's continuous or not, and I don't really need to know at this point. All I need to know is 1 minus x squared, so that's going to be an upside down parabola. So that's going to be less than 1. So here's 1. There's one breaking point. And then there's another breaking point. I don't want to make it look like an asymptote. And there's another breaking point at 2. So let's say it's going to be a downward parabola at 1. So it's going to look maybe something like this. At 3, it's going to be 2, 1, 2, 3. Let's do some kind of like line there. And then you have a linear equation greater than 2x minus 1. So I don't know. That's something it could look like, right? I mean, that's just a rough sketch, just to get an idea. The main important thing is, when we're dealing with the limit as x approaches 1 from the right, well, here's 1 and here's 2. What function are we dealing with 1 from the right? We're dealing with that function, that equation, right? So 1 from the right is just going to equal 3. All right? And you could basically say, because there's 1, what's to the right? And to the right is anything greater than 1, right? So that's why x is greater than 1. So that's going to be coming from the right. From 1 from the left, it's going to be values that are less than 1. So it's going to be this function. And so all we got to do now is plug in 1 in from there, and you get 0. So you can see my graph is going to be incorrect. And again, we're just plugging in the 1. The plus and the minus just tell us the direction that we're coming from. That doesn't actually tell us, like, make sure it's not the value, again, you're looking at. And then over here, we have x is equal, or what is the value of 1. So therefore, the left and the right-hand limit have to equal the same. And do they equal the same? Does the left and the right-hand limit at 1 same? No. So that limit does not exist. What about 2 from the right? So that's going to be values that are greater than 2, which is this like equation. Right? So 2 from the right is going to be plugged in here. So that's going to be 3. 2 from the left is going to be values that are less than 2, which is 3. Obviously, guys, if the left and the right-hand limit are the same, then that's going to equal 3. So now here's evaluating. Again, when you're evaluating, like f of 0, like what function? If here's 0, what function does that fall under? Which function does 0 fall under? This function, right? This quadratic one, right? Would you guys agree? So I just got to plug 0 into that quadratic, which gives me 1. So you just plug 0. 0 squared is 0. 1 minus 0 is 0. At 1, we got to figure out which function is defined. So at 1, it could either be this function or that function, right? It's either this one or that one. Well, that's not included. That is included. So at f of 1, you got to plug it into this equation again, which was 1 squared is 1. 1 minus 1 is 0. F of 2, again, could be either function. So you got to look at them and see which one's included, which one's not. This is included. That's not included. So you use that function. So you plug in 2. 2 times 2 is 4. Minus 1 is 3. And then last but not least, f of 3. So if you go over to f of 3, you guys can see we're using this last function. And again, remember, these graphs are wrong. But at least the last function, which is 3, all that is greater than 2. So 3 equals that. 3 times 2 is 6. Minus 1 is equal to 5. Anybody get them all right? All right, good. So, ladies and gentlemen, looking at this graph, or again, f of x equals y equals x squared. Hopefully you guys know this is going to be shifted down for 1, 2, 3, 4. And it looks something like this. All right, our discontinuities are going to occur when, so far when we looked at discontinuities, unless it's a piecewise function, the only way we know if something's discontinuous if it makes our denominator equal to 0, right? You guys agree that's the only other, except for piecewise functions, we've only looked at when something is 0 in the denominator. So in this case, do we have any sort of denominator here for any values? No. So if there is no discontinuity, this is a continuous function. OK? That's as simple as that. Continuous. So ladies and gentlemen, if we are not allowed a graphing technology, but we need to identify the limit for this, the first and foremost, the best thing we want to do is just like what we did last class period, is look for direct substitution. So if we go ahead and look for direct substitution here, -1 plus 4 times -1 plus 3, -1 plus 1, we see that we're going to have 0 in the denominator, right? So unfortunately, we can't divide by 0. So therefore, if we just looked at direct substitution, we're going to have indeterminate form. So therefore, direct substitution fails us. We're not going to be able to evaluate the limit when we're dividing by 0. So what we need to now do is look for some different algebraic techniques. And if you guys remember, our function is f of x equals x squared plus 4x plus 3 divided by x plus 1. Right? That's our function. Now, if you remember, we always want to look into, especially when we have rational functions, that's what our function is. What we need to do is look into simplifying that. And I noticed that in the numerator, I have a trinomial that I'm going to want to see if I can factor. So I'll go ahead and factor this into x plus 3 times x plus 1 divided by x plus 1. Right? By simplifying this, so by using factoring, I was able to simplify my function. So everybody see that? Just pass it over to the right, and they can pass it over that side. Now, by using the division property, I see that x plus 1s divide to 1. So therefore, I'm only left with the function x plus 3. Notice there is a constraint still of the x. X cannot equal -1. There still is a constraint of x cannot equal -1. But again, that's the value of the function cannot equal -1. We're not finding the value of the function. We're finding the limit. What is the function approaching? So I'm still going to use direct substitution here. I'm just going to plug in -1 plus 3. And what I obtain is 2. So therefore, the limit as x approaches -1 of this function, I simplify by factoring, and then I apply my direct substitution. I can't apply direct substitution from the onset because it gives me a 0 in the denominator. Questions? So step number 1, when substitution fails, look to factor. Factor. OK? Yes?
I'm sorry. You said x cannot equal -1. And then
Yeah, I understand that. It's kind of it's confusing the portion. This is basically just saying x cannot equal -1 because you can't if here's the function. Again, if anything else, I added it because I want if you see it, I don't want you to be confused on it. This is just saying f of x if you were to look at this function f of x equals x squared plus 4x plus 3 equals x plus 1. What is the value x cannot equal? -1, right? X cannot equal -1, meaning we can't do f of -1, right? So that's all I'm saying is you can't plug in -1 to find the value of the function. But we're not finding the value of the function. We're finding the limit, what the function is approaching, right? Because there's a difference. This function, at whatever that number is, let's just say 1, that function, f of 1, doesn't exist, right? X cannot equal 1, right? The f of 1 does not exist. X cannot equal 1. So whatever that function is, there's a hole there. It can't exist. However, the limit as x approaches 1 of f of x does exist. So you can still plug it in. I'm just relating the x cannot equal 1 for the function. But we're finding what is it approaching, which let's just say is 2. You see the kind of difference there? So I just wanted to put in that constraint because you probably will see it because mathematically that's a little bit correct. The next one, we're going to do the exact same thing. Here's -4, so we did the left-hand side. Now let's do the right-hand side. What is a number that is really, really close to -4, but from the right? Well, that's what we just did. From the right. Well, positive would be over here. All right, from the right, so think about it. -3, -3.5. Right, I know, it's tricky. -3.5, -3.999, I heard somebody say. So let's plug that in. X approaches -4 from the right. Let's do 3.999. Now again, I actually don't, oh, that's negatives, aren't they? Now again, I don't care what the value is, OK? You could have done 3.9 or 3.99. Doesn't really matter what your number is, because we don't care what exactly the value is. We just really want to know, is it going to be positive or is it going to be negative? So if you add -3.9999, add it to 4, you're going to get a positive or a negative value? Positive. And then if you have -3.999 to +1, what are you going to get? Negative. Guys, a negative divided by positive is negative. So therefore, it's going to go to -infinity. OK? Now, it might not be as obvious if there's holes or asymptotes going on here, right? Correct? Yes. So, but we see a trinomial, so we probably think, well, that guy's pretty tricky. When there's a trinomial, he probably wants us to factor it. So I'm just going to factor it just so I can have a better understanding. And I can see this is not too hard at factoring problems. If it was something that I really had trouble factoring, I would just plug it in and see if it actually worked anyways. But in this case, I can already see the factoring result kind of in my head. And I'm hoping that you guys can kind of factor this as well. So therefore, I see at x minus 1 or at x equals 1, there is a hole. And when x is equal to 4, there is a asymptote. Now, I have no idea what this graph looks like. Now, I'm sure you guys could plug it in your graphing calculator, and you guys could see what this graph looks like, right? I'm just going to make up some random graph, OK? This is not correct. But I know there's an asymptote at 4, and I know there's a hole at 1. So let's just do like 1. I have no idea what this graph looks like. All I know is there's a hole there and an asymptote there. Now, if I am approaching, if I was doing the limit from the asymptote, I'd want to see left or right-hand limit, right? I want to see where is it going, infinity or negative infinity. Would you guys agree? If I was testing the left or right-hand limit at the asymptote, I want to know, is it going up or is it going down? That's why looking at the graph would be helpful. However, I am checking the limit at 1. I'm checking the left-hand limit at 1. I don't really care what the limit, all I know is I just need to figure out what that value is of the function. So if I want to check this left-hand limit at a hole, all I'm going to do is just apply direct substitution with x plus 4 over x minus 4. So therefore, that's equal to, I'm just plugging 1 plus 5 over 1 minus 4, which equals a, that's not right. What happened? 1 plus 4. I'm doing the math in my head. Negative 5/3, which I wasn't too bad off of my thing. So that value is negative 5/3. That's what I am approaching, right? Yeah? What we can do is just choose smaller numbers that are really, really close. So rather than doing a whole table like we did, just pick one value that's really, really close. So from the left-hand side, we need to pick a value that's more negative than negative 3. So if I plugged in negative 3.001 and then negative 3.001 squared minus 9. So from the left-hand side, again, and we're only caring about signs. In the numerator is going to be a positive or negative number? Negative. In the denominator, if you have a number that's now larger than 3, right? Would you guys agree? This number squared is going to be larger than negative 3 squared. It's not by much, but it is. So that's not larger than 3 squared. So then minus 9 is going to give you a positive number. So if you have a negative divided by a positive, that's now going to be it's going to go towards negative infinity, which we were able to confirm in our table, as well as confirm in our graph. If you look at from the positive side, let's choose a value that's just to the right of negative 3. So negative 2.999. OK, again, our numerator is negative. In our denominator, we have a number smaller than 3 squared. So a number smaller than negative 3 squared, minus 9 is going to give us a negative, which will tell us it's going to go to positive infinity. So therefore, without even knowing what the graph looks like, without even knowing to graph it, or with the table, I can just pick values and use their signs to help me determine what the left and right-hand behavior is going to be of those limits. Yes? OK. Our direct substitution fails us, right? Because if I plug in 1, I get 0 in the denominator. However, I notice that x cubed minus 1, well, 1 is really cubed, right? It's a cube number subtracted from another cube number. So therefore, by using my sum and difference technique, which is if you have a cubed minus b cubed equals a minus b times a squared plus 2ab plus b squared. So by using that, I can identify this to be x minus 1 times x squared minus 2x plus 1 all over x minus 1. That's plus, sorry. So by using this factoring technique and using a to be x, or a to be x, and b to be 1, I just factored out the rest of this. And what's nice about this is, again, you guys can see my division property divides those out. right? And remember from this, what did we say our solution was? The f of 1 was undefined, but f of 1, do you guys remember the graph? I think it was 3, right? Huh? Was the limit, but when we did that? Yeah, let's see. My x minus my 1. X minus 2, 1. What did I plug in wrong? A minus B. Oh, I'm sorry. It's AB, not 2AB. Sorry about that. Sorry about that. It's just x1. I wrote in the wrong formula. I was thinking I'm teaching the sum of two. I'm teaching perfect square trinomials and pre-calc, so I got confused with the 2AB. So it's just going to be x squared plus x, or it's just a squared plus ab, not 2ab. ab plus b squared. So therefore, you guys can see that it does exist. It does add up to 3, which is exactly what we found out, what we found it to be when we did tabular method and so forth. Yes?
Is B 1 or negative 1?
B is going to be 1.
Why?
It's because it's a cubed minus b cubed. Okay, kind of think of it like that. First thing we want to do again is, we know that whatever is going to make our denominator equal to 0 is going to be a discontinuity. So we're going to want to basically set our denominator equal to 0 and go ahead and solve. All right. Now again, we're looking at a factoring problem where we notice that a is not equal to 1. However, any trinomial is going to be broken down into two binomials. And if we want those first two terms to multiply to give us 2x and 2x squared, then we could say 2x times x will give us 2x squared. The next term is we want our two terms to multiply to give us negative 2. So therefore, we basically have negative 2 and positive 1, or negative 1 and positive 2. Well, we want them to add up to give us a positive 3x. So therefore, I want the larger of my two products to be positive, because I'm going to add them together. So if I kind of do some thinking here, 2x times x is 2x squared. Negative 1 times 2 is negative 2. And then if you multiply and combine the inner and the outer, what you guys notice is those add up to give you positive 4x, right? So it's just some thinking in your head, some basic factoring. Now, let's rewrite the equation in factored form. F of x equals 5 over 2x minus 1 times x plus 2. Does anything divide out in my numerator and my denominator? No. Since these cannot be divided out, these are still discontinuities. So we're going to say x cannot equal negative 1/2 and x cannot equal negative 2. So those are my discontinuities, and they are asymptotes. Okay? Wholes can be divided out. Asymptotes cannot. So regardless of trying to find the limits or anything else, we're just trying to find the discontinuities. All we simply need to do is, again, try to simplify our function by factoring. So this is the difference of two squares, x minus 2 times x plus 2, all over x minus 2. What you guys can see is now my expression in my denominator is exactly the same as my expression in my numerator, right? So those, therefore, they divide out. Now, again, though, that discontinuity is still there. X still cannot equal 2, because when x equals 2, my function is 0 in the denominator, and that doesn't work. However, since it's being divided out, when that occurs, that is what we call a whole. Okay? So the whole occurs at 2. So basically, x cannot equal 2, and that is a whole. So I'm going to ask you, define the discontinuity, and then tell me where there's a discontinuity, and then classify the type of discontinuity. So again, guys, when we're looking for our discontinuities, anytime you see something that can be factored, let's factor this out. f of x equals x minus 1 over difference of two squares, x minus 1 times x plus 1. Notice the x minus 1s divide out. So we're left with f of x equals 1 over x plus 1. So again, just a reminder, if it can be divided out, it is a whole. So you're going to say x cannot equal 1, because that's a whole. And x cannot equal negative 1, because that is a asymptote. Okay? So you guys can see I have 3 different denominators. I have 2 minus x. I have 2. And there's a denominator 1 there. Right? So what I'm going to want to do is I can't plug in 0, because if I plug in 0 there, that makes the whole denominator 0. It's undefined. However, I can eliminate the denominators by multiplying the top and the bottom by my LCD. So the LCD is going to be the common, basically the least common denominator. So if I have 1, 2, and 2 plus x, I can write my common denominator as 2 times x plus 2. Just rewrite that as x plus 2. It doesn't really matter for me. Okay? So that's going to be my common denominator. And I don't really need to write 1, because 1 obviously divides into it. But x plus 2 divides into that, and 2 divides into that, because they both flow it. So now I'll multiply the top and the bottom by 2 times x plus 2. Okay, now watch. Oh, and you got to remember when you're multiplying this numerator, this complex fraction, you got to remember you're multiplying the top and the bottom. So a lot of times we'll just write it twice. Okay, you're multiplying basically every term. When you're trying to get rid of your fractions, you're multiplying everything times your LCD. So what happens when I multiply 1 over 2 plus x times 2 times x plus 2? Well, these are the same. They're just switched around. So since this is in the denominator, that's in the numerator, they divide out to each other, right? So that's going to just leave me with 2. And then minus. Now here, you can see that the 2's divide out. And again, guys, if you did this correctly, your denominators are always going to divide out, right? Because by choosing the LCD, you're choosing numbers that your denominators divide into, right? So if you don't get rid of your fractions, then you obviously did something wrong. And then the denominator, I'm going to have 2 times x times x plus 2. Now, I would recommend leaving it just like that, not doing anything else, not simplifying your denominator, because my numerator, apply distributive property. You guys can see here now the 2's divide out. Subtract out. And then we're left with a negative x over x. Those also divide out. And therefore we're left with a negative 1 over 2 times x plus 2. Now, after simplifying this, now can we directly substitute? Now can we directly substitute? Yeah, now it's perfect, right? We just had to simplify this a little bit. Simplify as x approaches 0, so we're just going to plug that in. So we have negative 1 over 2 times 0 plus 2. 0 plus 2 is 2 times 2 equals negative 1/4. Check for this. This one again. Again, guys, identifying the LCD. This does not have a denominator, so that's 1. And again, the least, think about the LCD as like, what's the least common denominator of 4 and 3? Well, the easiest way to find the LCD of 3 and 4, if 4 and 3, is just to multiply them. 4 times 3 is 12. 4 divides into 12, 3 divides into 12. These, they're kind of a little bit harder as far as finding the multiples of x minus 4, right? Or the multiples of x plus 4. So the easiest way to find the least common multiple is to just multiply them. So the LCD here is going to be x minus 4 times x plus 4. One we don't really care so much about. So I'm just going to multiply everything by x minus 4 times x plus 4. Everything. Okay, by doing that, you guys can see these x minus 4s divide out. You can see these x plus 4s divide out. And so therefore, we have x plus 4 minus 2 times x minus 4 all over x plus 1 times x minus 4 times x plus 4. All right. So we go ahead and simplify this. Here we're going to be left with, this should have been a, let's see, that's going to be a negative x. So we distribute this. So we'd have x plus 4 minus 2x plus 8. No? Oh, okay. Okay, notice here, that's going to go to 12, and that's going to go to negative x. Now, does anything divide out in my numerator and my denominator? Does anything divide out? No. So guys, what happens when we still plug in negative 1? When we evaluate for negative 1, what is that going to be? 0 times that is 0 times that is 0. So even though we went through all the mathematics of eliminating the LCD, we still didn't do anything mathematically that could have simplified this. So therefore, this limit still does not exist. OK? All right. So if we needed to do a problem like this, now I'm going to show you guys the graphical representation, so it kind of makes sense. Even though once you guys get a little familiar with this, you should be able to quickly look at this and say, this is exactly what the limit is and so on and so forth. But first of all, let's go ahead and practice graphing this. OK? Now remember, guys, when you're graphing a piecewise function, this is a lot of times what I teach in pre-calculus, is there's going to be two different functions. You have a function y equals 1 and y equals 0. OK? So we basically just need to graph these two different functions. Each of these represent a different function. So you can graph them separately and then kind of put them together. So how do you graph y equals 1? Well, just remember we talked about this. Y equals 1, we did that over there. It's just a nice solid line. However, there is a constraint. It says graph y equals 1, but x cannot equal 2. So therefore, there's going to be a little hole. OK? Now the next one is 0. So graph y equals 0. Well, that's going to be like the x-axis, right? But it says only graph it when x is equal to 2. So if x is only equal to 2, that means to represent that, we're just going to have to represent that with a dot. Because it's not like it's literally we took everything away from the line and just only equaled it when x is equal to 2. So technically, we have this graph that looks like this. That's what the graph looks like. So the piecewise graph looks just like that. OK? Now, hopefully, soon enough, you guys will be able to visualize this graph. All right? That's our goal, is to get you guys so good you can visualize this. So now, if I believe my limit was going to ask you, what is the limit as x approaches 2 of f of x? So again, we just need to look at the left and right-hand limits, right? From the left, what value are we approaching? From the left, what value are we? OK. Remember, its limit as x is approaching 2. What we're looking for the height. OK? The x values goes along here. This is the f of x values. What value of f of x are we approaching as x gets closer and closer to 2? So here, x is negative 1. Here, x is 0. Here, x is 1. Here, x is 1.5, 1.5. As we get closer and closer, what value is it approaching? 1. From the left, what value is it approaching? 1. And guys, if you're getting confused on it, I mean, you can just look at like the table of values, right? I mean, if you, well, actually, you don't need to look at table values. All the value is 1, right? However, here's a nice little interesting fact. What is f of 1? What is the value of the function? I'm sorry. What is the value of the function at 2? Well, there's a hole at 1. So it can't be that. What is the value of the function at 2? Yeah, it's 0. When x equals 2, the value of the function is 0. Right? So this is really important because, guys, the value of the function can differ from the limits. Because, again, I have to drill this into your head. The limit is what the graph is approaching. It's not the value of the function. The value of the function is 0. But what is the graph approaching? 1, right? And it has to approach from the left and from the right. Okay? So if we're going at different values, or if it's only one-sided, then the general limit doesn't exist. Does that make sense? Okay. So you don't need to graph this, but here is 0. Here's the limit that we're trying to find 0. This function is for all the functions that are less than 0. So that's going to be your left hand. And then this function is for all values that are greater than 0. So that's going to be your right hand limit. Would you guys agree with me? So if we're going to say the limit as x approaches 0 from the left is going to be of x plus 1. And the limit as x approaches 0, that has to equal the limit as x approaches 0 from the right, which is going to be x squared plus 1. Okay? Now, it really doesn't matter. The left and the right is really just saying that that's like the direction. So all we really need to do is do 0 plus 1 has to equal 0 squared plus 1. 1 equals 1. So therefore, the limit is obviously, they both are equal to 1. That is going to be our limit of our piecewise function. Does that kind of make sense? For the limit to exist, the left and the right hand have to be equal to each other. Look at the graph. For the limit to exist, they have to be equal, right? Basically on this one, guys, it's again evaluating us for x as x approaches pi for over a tangent of x. So again, we can look at this and just do applying direct substitution. So therefore, I now need to identify the tangent of pi. Remember that the tangent of any angle is basically equal. And when looking at a triangle, it's opposite over adjacent. But when we're looking on like the unit circle for coordinate points, it's going to be the y coordinate over the x coordinate. So if we look at the unit circle, and we look at the angle pi, starting at our standard position, pi is going to be over here. If here on the unit circle is 1, 0, this point is -1, 0. So therefore, what we'd have is -1 over 0, which is just equal to 0. And that's basically it. So you can use the unit circle. You could also look at the graph. Just real quick, if you were to look at what tangent looks like, you could graph that if you had a graphing calculator available to you. That's at pi halves. That's at 0. Remember, the period is pi. And so at pi, you can see that the graph crosses at 0 if you were to graph it as well. Again, we can kind of go back to our limit laws, our limit properties, to help us with this. Remember, our properties of limit says if I have limit as x approaches c of b times f of x, that's the same thing as b times of b times the limit as x approaches c of f of x. Right? Yes? So what I want you guys to understand here, and again, remember also another rule, or another just idea, is if you have 1/2, and you multiply by 1/2 by 4 over 4, I'm going to get 4/8. Do you guys agree with me that 1/2 is equal to 4 over 8? So as long as you multiply by the same number, you're OK, right? Now, the only rule that we have is that the limit as x approaches 0 of sine of x over x is equal to 1. Well, guess what? That rule works for x approaches sine of 2x over 2x. Limit as x approaches 0, sine of 3x over 3x. It works for all of them. It doesn't matter. And let's go and look at this graph. Let's go ahead and copy, or let's just put in 2 and 2. Oops, what is this? Do you guys see right now how it's still at 1? Right? Let's go and put in 5 and 5. If I change this to 5 over 5, it's still approaching 1. Right? So all I need is this to be 4x over 4x. Right? So I need my 4 to be in my denominator. So if I multiply by 4 over 4, basically now what I have is the limit as x approaches 0 of 4 sine of 4x over 4x. I can now group this together and kind of take out that 4. So if you multiply this on the outside, you can multiply on the inside, right? You can multiply it on the inside. I want to group this together because what's the sine of 4x over 4x? What's the limit of as x approaches 0 of sine of 4x divided by 4x? That's now going to be equal to 1. So we basically have 4 times 1 equals 4. So first thing, would you guys agree with me, at least in our vision, we can't apply direct substitution here, right? So we agree with that. That'd be the first thing. The second thing is we want to get sine of x over x and 1 minus cosine of x over x, either one of the two or both. So let's look at some manipulation. Well, I can rewrite 2x squared, can I? I can rewrite that as 2x times x. Yes? Now, is it OK for me then to say, well, I'll group that, and I'll group that? I mean, is there anything wrong with that? They're separated. They're all separated by multiplication. So now what I'm going to do is I'm going to rewrite this as basically the limit as x approaches 0 of sine of x over 2x times the limit as x approaches 0 of 1 minus cosine of x over x. We've done that before, right? I mean, you're just multiplying. If you have two limits, you can just multiply them. That's perfectly fine. You can break them apart. Then, even though you don't really need to do much work after this because that's going to go to 0, just to practice a little bit more, we could take out the 1/2. I'm just going a little overboard just because I know it's still new. But guys, we have 1/2. What's the limit as x approaches 0 of sine of x over x? What is this? 1. What is this? 0. So we could have easily finished this problem 15 seconds ago, right? But just to make sure you guys remember your limit properties, that's why I kind of spent a little bit more time on it. Okay? But let's just kind of go back over to limits. Let's not forget our limits. And let's look at the limit as x approaches infinity. Okay? So as x is going to the right, you can see that the graph is shooting up towards positive infinity. And as the limit as x approaches negative infinity, so what basically you guys can see, these keeps on getting to be larger and larger fractions. And larger fractions are going to converge on the number 0. So as the limit as x approaches negative infinity is going to equal 0. Okay? And then last but not least, let's look at the limits. So limits, we can take the limit here of as x approaches infinity from the, let's go from the positive side. So you guys can see as the limit is approaching 0 from the positive, you can see that we're going down to negative infinity. And the limit as x approaches infinity, so as we're going to the right, this graph is increasing, going to positive infinity. So again, going into limits here, we got to look at what transformations are happening. OK, this is being shifted left 2. Now remember, here's the parent graph, right? OK, so it's being shifted left 2. So now it looks like this. And then it's, so the asymptote, which is that 0, is being shifted left 2. But then it's also being reflected. So as I'm approaching negative 2 from the right-hand side, you guys can see that the graph is going up to infinity. So we look at 2ax plus b and negative 2, and we realize that we have all 3 continuous functions, right? But we're looking for 2 variables. Now, I'm going to pose a question. And actually, I'm just going to randomly pick on somebody, because you guys are pretty tired and quiet. So, Edward, when you have 2 variables, what algebraic process could you use to solve for 2 variables? It's from your algebra days. Systems of equations, right? So I already know that there's 2 variables, unknowns. I already know that, hey, if I need to solve for 1 variable, I need to have 1 equation. I can use inverse operations, right? If I have 2 variables, I know I'm going to have to use systems of equations. So I've already just kind of planted that in my head. And one thing actually I remember my college professor told me is, like, when you have 2 variables, you need 2 equations. If you have 1 variable, you need 1 equation. 3 variables, you need 3 equations to solve. Okay? So automatically, I know that I'm going to have to probably be using a system of equations to go ahead and solve this. Then again, the next thing that I notice is that there are 2 points where this function can be discontinuous, right? There's 2 functions. There's 2 points. You have, let's see, graph looks something like this. You have 2, then you have this line, and then you have like negative 2. Right? It looks something like that, roughly. I didn't even check the numbers, but it looks something like that. So there's 2 points where it could be breaks. So we need to find the values of a and b where it's going to connect, right? So it's going to be continuous. That's what the question is asking. So again, first thing we need to do is evaluate for the limit at x equals negative 1. We need to make sure that limit exists. So therefore, to do that, we need to check the limit from the left-hand side and from the right-hand side. So let's do limit from the left and the limit as x approaches negative 1 from the right. Well, from the left is going to be the values that are less than negative 1, which is just 2. The limit of any constant is obviously just going to be 2 there. And then from the right, we have ax plus b. So that's going to be ax plus b. Well, if we evaluate here negative 1, that's going to be a times negative 1 plus b, which equals negative a plus b. Now again, for our limit, let me actually write this down. For our limit as x to approach negative 1 to exist, 2 has to equal negative a plus b. Right? And we're just going to keep that. We're going to store that. Now, let's look at the next break-even point. At 3, the limit as x approaches 3 from the left. So 3 from the left is going to be the left is going to be ax plus b. Evaluate for the limit 3. (3a plus b). Does everybody follow? Limit as x approaches 3 from the right is just negative 2. Again, for the limit as x approaches 3 to exist, the left and the right have to equal each other. 3a plus b has to equal negative 2. Right? So now we have two equations where we know that the limit needs to exist. So for this to be continuous, limit at 3 needs to exist, and the limit at 2 needs to exist. I'm just going to rewrite this as negative 2 equals 3a plus b. If that's OK with you guys, just using the reflexive property. So therefore, what I have is system of equations. I have two. Actually, let's rewrite it. Actually, I'm going to leave that like that. I'm going to rewrite this one. So I'll have negative a plus b equals 2. And I have 3a plus b equals negative 2. And then to solve the system of equations, I could use substitution, or I could also use elimination, or I could just subtract them. So therefore, I figure out a is equal to negative 1. Where? Yeah, I'm subtracting each of these rows. Here. That's the two equations, right? Do you see these two equations? Do you agree with me? Do you have these two equations? OK. So these are the two equations in my system. I need to eliminate b. Well, I can't add them, right? Because that's going to give me 2a and 2b. So I have to subtract the equations. So I'm going to subtract the bottom equation from the top equation. So it's negative a minus 3a, it's negative 4a. B minus b is 0b. 2 minus a negative 2 is 4. Try your way another. Do substitution your way. Right? Substitution solve for a or b, and then plug it in. Just try doing that, just to verify. All right, I'll go and take a look at your work, and I'll advise from there. So now we know that a equals negative 1. So now I can just plug it into either one of my equations. I'll plug it into the top. So therefore, for the function to be continuous, a has to equal negative 1, and b has to equal positive 1. We have three equations, right? We don't know what this graph looks like. But for visual purposes, let's just pretend we know what this graph looks like. So at 1 and at 2, those are kind of like our breaking points. So I'm just going to say there's, here a graph looks like this. Then a graph looks like that. That's open. And that's open. And then a graph looks like this. So basically what we're trying to do is we're trying to connect these three graphs so the graph is continuous. That's like what we're trying to do. We're trying to find the values that are going to make these connections. So basically there's two values that we want to have connected at x equals 1 and at x equals 2. Do you guys see that? So for them to be connected, we know that the left and the right-hand limits need to be the same. So we'd say that the limit as x approaches 1 from the left of f of x has to equal the limit as x approaches 1 from the right of f of x. So we basically want to make sure these are the same from the left and right hand, because right now they're not the same, right? So to make them the same, we're just going to do, so x plus 1 has to equal ax plus b. Now you evaluate in the limit. So therefore, you're going to plug in 1 plus 1 equals a times 1 plus b. So your first equation is 2 equals a plus b. For this next equation, for the next thing, we want to make sure the left and right hand limit at 2 is going to be the same. So again, I'll just write the limit as x approaches 2 from the left of fx equals the limit as x approaches 2 from the right of f of x. So the left-hand limit is ax plus b. And the right-hand limit is going to be what represents 3x. Then I plug in my new value that I'm trying to make them connect at, which is 2. So it's going to be a times 2 plus b equals 3 times 2. which is 2a plus b equals 6. So there's one equation. There's my other equation. Now that I have these two equations, I can just use a system of equations to solve. A plus b equals 2, and 2a plus b equals 6. So I just rewrote them. You don't need to rewrite them, but that's the way I like to do it. And then I'm going to use elimination. So what I'm going to do is I'm going to subtract the two. So by subtracting the two equations from one another, I get negative a minus 0b equals negative 4. So it's negative a equals negative 4. Divide by negative 1, divide by negative 1, a equals 4. And then now that I know what a equals 4 is, to find out b, I just plug it into one of these other two equations. So let's plug it in here. Negative 4 plus b equals 2. Add 4, b is equal to 6. Was that the answer? Negative 4 and 6? No. What happened?
It's negative 2. B is negative 2.
But a is 4. Oh, it's positive 4. I got onto yeah. It's positive 4, so you're subtracting 4 on both sides. B equals negative 2. Okay? And that's it. Again, the thinking, ladies and gentlemen, just the thinking. We have two functions, right? Is this function continuous on all x? No. So there could be a discontinuity here, right? Because remember, the question is asking, I didn't write down the question. The question is asking, what are the values of k that are going to make this function continuous, right? So we're looking for the value, though, that's going to make this continue. What value is going to connect, what value is going to make this continuous? Because we know right now this function is not continuous, right? And if you guys remember, I think this is the one that I think, yeah. All right, actually, I'll do that when we finish it. So this value we know has discontinuities. We just don't know which ones they are. And we know that this discontinuity happens at negative 3, or at least one of them, right? So let's go ahead and first evaluate the limit as x approaches to negative 3, because that's where it's going to be. That's not going to be the value. So I have 2x squared plus 5x minus 3 all over x squared minus 9. Now, we need to figure out our discontinuities, and that's something that you guys practiced in your last homework as well as what we did on our quiz and what we've done before. So you have to know how to factor. I can see my leading coefficient is a 2, so I know my factors are going to be 2x and x. I automatically see the denominator as a difference of 2 squares, so I like seeing those because those are easy to factor, right? So now I just need to figure out what two numbers multiply to give me negative 3 but are going to add to give me a 5. Well, I know that it needs to add to give me 5, so if I did 2 times 3, that would give me positive 6, right? And if I multiplied x times negative 1, that would subtract 1 and give me 5. And negative 1 times positive 3 is a negative 3. So by factoring, I can see that my solution up there is right there. And I can always verify my factoring. Just make sure you FOIL it back out, make sure it works. Oh, sorry, I switched those. That's positive, that's negative. Right? OK, so we evaluate so now let's simplify the limit using some limit notation here. I'll bring this back down. I know those are going to divide out, so I'm left with 2x minus 1 over x minus 3. Which now I can evaluate for, which would be 2 times negative 3 minus 1 over negative 3 minus 3. Let's see, that's going to be a negative 7 over negative 6, which equals 7 over 6. All right, so let's first of all talk about discontinuities again, because I talked about it in last class period, but I didn't go over this. So we have two discontinuities. We have a discontinuity at x equals negative 3, because negative 3 makes that 0. And we have discontinuity at x equals 3, because 3 makes that 0, correct? Since this is factored out, since you can factor this out, that's what we call removable. This discontinuity is not removable, so that is That's a non-removable discontinuity, correct? All right. However, if we look at 7 pi at the limit as x approaches -3, we get 7 over 6. Well, again, we need to now make sure that that is going to be equivalent to our other function from the, you could think of it, it's not really from the left or right side, but we know it has to equal that value. So we can just say k is equal to 7 pi over 6. So again, our algebraic method of determining the limit is we take the highest power in our denominator and divide each and every term by that highest power. So I'm just going to rewrite this as x approaches -infinity. So I'm going to have 5x over plus 4 over divided by 7x cubed over plus 2x over minus 1 over. So I'm just going to write x cubed, x cubed, x cubed, x cubed, x cubed. OK? Now what we basically want to do is evaluate this and see what everything, actually let's go and simplify this to see where everything goes to. So this becomes 5 over x squared plus 4 over x cubed divided by 7 plus 2 over x squared minus 1 over x cubed. OK? Now, any number divided by a variable to raise a constant goes to 0. 0. That goes to 7, so that remains 0, 0. 0 over 7 equals 0. First of all, when you have a limit and you're taking it to infinity, we're looking basically for what the horizontal asymptote is, where the graph is going to approach. The first thing I want to do is always rewrite my function in descending power order. OK? So now you guys can see I can compare my degrees. I have 3 halves and 2. 3 halves is the same thing as 1.5, right? Now, the degree in my denominator is smaller than my degree in my numerator. That tells me that the horizontal asymptote, if we were just talking about horizontal asymptotes, would equal y equals 0. Anytime the degree in the numerator is less than the degree in the denominator, y equals 0 is your horizontal asymptote. So if that's my horizontal asymptote, then the limit as x approaches infinity of that is just going to equal 5 minus 2x to the 3 halves over 3x squared minus 4 is just going to equal 0. Done. First of all, remember that the square root of x equals plus or minus x, right? Now, since we have x approaches infinity, we're only going to be dealing with the values of x as they're getting more and more positive. Does that make sense? OK. So let's go ahead and divide what we're working with here. So I'm going to divide both of these numbers by x squared and x squared. But remember, those x squareds is under that square root, right? So if I'm going to divide them for these two numbers, I got to make sure that I include that as far as under the square root. X squared minus x over square root of x squared divided by square root of 7 over x squared plus 6 over x squared. Now, as we already mentioned, the square root of x squared, fortunately for us, ladies and gentlemen, we know is going to be plus or minus x. Since x approaches infinity, we can just simplify that to be x. Now, actually, you know what? Yeah, all right. All right, I'll rewrite that. OK, so now let's go ahead and determine where everything is going to. 2 over any kind of number as it keeps on getting larger and larger and larger is obviously going to be going to 0. That's going to go to 1. So right now we have 0 minus 1 all over the square root of any number divided by x raised going to a higher power is going to be 0. It is 6x squared. Thank you. I was wondering. So those divide out, so that's going to be plus 6. So therefore, we have negative 1 over the square root of 6 is going to be our value. And that is exactly what I got. OK? OK. If you guys look at this, one thing I want you guys to go through, which a lot of you had trouble with on your last quiz, was using the properties of limits. Remember, we can break apart, properties, and that was one of the things that I'll explain to you. I'll show you guys in your work. But if you guys kind of look at this, we can break this apart into the limit as x approaches infinity of 1 over x times the limit as x approaches infinity of sine of 2x. Because do you guys agree? It's like saying 3 divided by x is equal to 1 over x times 3. Do you guys kind of see how I just did that? Now basically, actually, let me maybe not even go a little bit too fast. You can break that up into the limit of 1 times x times the sine of 2x over x. Then it makes sense to say, oh, when I have the limit of the product, if you guys remember your rules of limits, what that means is I can basically take the limit of them separately and evaluate. All right. Now, this one probably would have taken, I actually wanted to go over this before giving you your homework, so I kind of apologize in that regard. First of all, we know what this limit's going to be, which is 0. Now, we have this limit of sine equals 2x as x goes to infinity. And we didn't get to talk about this, and I apologize. But if you guys look at this, sine of 2x tells you, that's going to actually not change the amplitude. That changes your sine of 2x. That's going to elongate things. But if you guys remember, sine looks something like that, right? So as it goes to infinity, does it ever approach a number? No, but you got to think, what does it approach? That's what it hits. That's the max and the min. But what does it approach a number? Remember, asymptotes are like, if you think of this, it's approaching 0, but it's never going to get to 0. Is this approaching anything, or is it just bouncing up and down between 1 and negative 1? It's just bouncing up and down between 1 and negative 1, right? So the sine of 2x does not exist. However, if we, in this case, we have 0 times does not exist, you guys will see that this function, actually, when you graph it, is going to go to 0.